right, thanks a lot for being here. So this is going to be more focused on dynamics. So this work was done at LANL-SkyrmionWorkshop with various collaborators over the years. So Cynthia Reichhardt, she's back there. Tom Ray is a very talented graduate student of ours, who's home base with Notre Dame. Sebastian Diaz is also a graduate student at this work. I think I'm helping you subscribe. Sebastian Diaz, graduate student at UC San Diego. Vlad Saxena, chairman here. So people are pretty familiar with skyrmions. So predominantly, we're going to consider the skyrmions in this talk is to consider them as a particle rather than say a wall of like the actual texture. But we'll also look at that as well. And luckily, I don't have to go too much background in this, but people have seen lots of skyrmions in various places, and you can see that the lattice structure changes from triangle lattice to individual skyrmions, and they seem to be set in motion through the application of a current, or it could be electric field, and so on. Here's an example here of electron going through the spin texture of the skyrmion. So how do you tell your skyrmions are moving? Well, you can directly visualize them with lens microscopy, have some neutron scattering. But the other way is with transport by looking at changes in the topological Hall effect. Now, we've previously done a lot of work in superconducting systems, where again, you can apply current in your vortex, in that case, with the pin. But those systems, in some sense, are much easier to understand to transport because when they're superconducting, there's no dissipation, but once the vortex moves, we have this dissipation, so we just measure the voltage. These systems are always dissipative, so just the skyrmion moving doesn't necessarily change the voltage, but you can see small changes in the topological Hall effect. And Lynn showed that you can essentially make a skyrmion velocity versus applied force curve, and this would be equivalent current to the beginning of skyrmion, and then the skyrmion starts to move very rapidly. And then the other way I said to get these velocity force curves is just with direct observation. So here's the fairly applied pulse. You can just then measure your skyrmion velocity versus your critical current out of the group of Oregon. People have done this as well. And as I mentioned previously, from the superconducting systems, you have a vortex lattice, you apply a current, and then you can measure a voltage response. And that will tell you the any current. But there's also been lots of work in trying to understand exactly the different kinds of motion that voltage superconductor will have. And you can get those from looking at, say, the differential conductivity and noise fluctuations and so on. Another reason is why you care about skyrmion dynamics. Well, there's two reasons. One is the application reason. Many possible applications you need to move skyrmions around, have them in for a while, and then or you want to do some computation. So you got to understand the dynamics of those very well. And the other reason, of course, probably what is more motivating to us is that they really represent a new class of dynamical systems. So there's many examples of condensed matter systems where you have a collection of interacting particle-like objects. Here, of course, is the superconducting vortex lattice. Here's a colloidal lattice. These are charged solids on the micron scale. And people can look at, say, 2D melting. You can look at the system coupled to a substrate. You can apply local perturbation. You can look at glassy physics, shearing, and so on. And a lot of these systems, either they would be overdamped or, say, underdamped. But the dynamics of the skyrmions is going to introduce something really new that hasn't been studied so extensively, and that is the role of the magnet force. So going back to superconductivity, we also showed you that there's a big bucket of work on how to control vortices, control the geometry or the motion. And another idea is, can some of these concepts be applied to the skyrmions as well? So here's an example of a case where they have a periodic array holds in a superconductor the large dots of the vortices, and then you have a one-to-one matching, so you can look at commensuration, incommensurate transitions, square vortex lattice at higher fields, you get a triangular vortex lattice, you get submatch. And this is the measure of the critical current versus applied field. And these peaks correspond to when you get nice ordered vortex lattice. You can also make what's called vortex ratchets, where you have some asymmetry engineered on your sample. You put a triangle magnetic dots, or you get extra surface, and then they apply some AC shaking, and you end up getting a preferred motion of your voices. And one could ask, could something like that be done for Skyrmions? So I'll approach this two ways. I'll first review the work with the continuum model, and then we'll go to the particle-based model. So the continuum model is basically just Gilbert equations. And then if you do that, this is what you get. You get a zero field, you get a nice strike phase, and in finite field, you get the Skyrmion phase. So now the next picture, what we're going to do is we're going to go, okay, let's ignore the spin degrees of freedom, and we'll just say this is a particle and it has an equation of motion. So the advantage of this is that we're going to be able to do a much larger number of particles, a much larger number of times. The disadvantage is that certain internal modes of vibration or oscillation. So what would here's an example of the equation. Skyrmions have been simulated with a particle-based description, and the white dots here will be repeating. So here's the equation of motion for the Skyrmion. So the first term here is the damping. The second term is the Magnus gyroscopic term. This will be the Skyrmion force. We assume that it's impulsive. The Skyrmion will form triangle lattice. There will be some force from the pinning, and then some force from the driving. So this equation can also be used to describe vortex dynamics in terms of superconductor. And in that case, it's true that in a superfluid or superconductor, you would still have this Magnus term. But generally, this term is so much larger that you just don't see effects of the Magnus term in type 2 superconductors. But for a Skyrmion system, these terms can be on the order of 1, the ratio can be 1 to 1 or higher. So that's something that's quite different than you'll see in a lot of the other particle-based systems that have been studied. And to give you an idea why that will change a lot of the dynamics of this compared to overdamped systems, is here we have an example of, we have a pinning site here, here's the pinning site minimum. Down here is the overdamped version of the system. And so your particle comes along, it wants to move right to the lowest energy state because the velocity is aligned with the direction of the force. On the other hand, the Magnus term, remember we had a cross product in it, is that the force is pointing towards the potential minima, but the Magnus term creates a velocity component that's perpendicular, so it has a tendency to spin around pinning sites. It also affects the dynamics of the particles themselves. So on this side here is the overdamped case, and this is the Skyrmion case. And we just put these particles together, and we're going to let them expand out. So this is what you see. In the overdamped case, just all forces go radially outward. On the other hand, for the Skyrmion case, you get this rotation. So again. So it was mentioned earlier about Matisse about the Skyrmion Hall angle. So because of this Magnus force, if you have just have a Skyrmion by itself, and it's not interacting with pinning of the Skyrmion, to apply a drive, the Skyrmion doesn't move in the direction of the drive, but it will move at an angle with respect to that drive. And that's the Skyrmion Hall angle. And the bigger the Magnus term, the bigger the Skyrmion Hall angle will be. So what we're going to do is we're going to do a simulation of particles of the Skyrmions, random pinning sites, and we're just going to apply the drive and see what happens. So this is the Skyrmion velocity in the direction of drive, the red curve. This is perpendicular to the direction of drive. So if it's an overdamped system, this would be 0, and it would only have velocity in the direction of drive. We have a Skyrmion angle in intrinsic angle that we know from our parameters we put in, it should be about 80 degrees. So what we see is you have a region where you have a finite drive, like it's pinned, and then they start to depend, and then they move on. And if you measure the Skyrmion Hall angle, what you see is it starts off low, gradually increases, and then approaches the dash line here, which is the clean line. I'll say a little more about this effect later. So then here's some further studies on this. We then went back to look at this a little bit more carefully, and this is the ratio of velocities perpendicular to parallel directions. This is the driving force. This is done for different intrinsic Hall angles we put in. And what we always see is the same trend, that there's a sort of a linear regime here, when the drive is increasing, and then when it's fast enough, you get a saturation to the Skyrmion Hall. And this is for different forces, and this is for different amounts of pin size. And this is to show you the case. So we can look at two limits. One is the single, or three limits: the single particle limit, the elastic lattice limit. The other is what we call the plastic flow limit, where we have the pinning is strong enough to disorder the Skyrmion lattice. When you apply drive, you indicate some guys are pinned temporarily, and then they move, and then as you go faster and faster, eventually go on. So let me skip this real quick and jump ahead. So why do you have this Skyrmion Hall angle? So in this case here, right, the drive is in the y direction, so the Skyrmions, if they don't interact with the pinning site, they move at an angle about 80 degrees with respect to the drive. So when they hit the pinning site, you end up getting this curving motion as we saw, but as it goes around, you end up getting this shift. So this is the dash line. This line indicates the trajectory of the Skyrmion we take without interacting with the pinning site. There's a couple of things to notice. One, if you come in from the pinning site from this side, at a certain drive, you can spiral and get pinned. If you hit the pinning site from down here, your shift isn't so big. The faster the Skyrmion is going, the smaller the shift. So if you have a bunch of pinning sites, keep hitting these things, you get this gradual reduction of your Skyrmion Hall angle. And this is a plot of the impact parameters. So you have a pinning site. Your Skyrmion's coming in from the left or the right. So this is the shift that your particle will get. And the overdamp limit is symmetric. In other words, if it comes in to the right, it's shifted about the same amount as shifted to the left, but just in the opposite direction. On the other hand, in the Skyrmion limit, you have an asymmetric shift. And this is so as you go through the pinning site, depending where you come in, you'll get a different shift, and that will give rise to the change in the Skyrmion Hall effect. And the faster you go, right? So here's a low drive, so you have the biggest shift, and the faster you go, the smaller the shift gets. So the previous work is at zero temperature, but also what happens at finite temperature? So this is a plot of the Skyrmion velocity for different temperatures. So at zero temperature is the blue curve. You have extended range with the pin, and then you have critical pinning and slide. Now you start increasing temperature, then you start getting your pinning force decreases, and you also get some more curvature of velocity force curves. I'm going to have a clicker here. So the plot here, the blue plot is the Skyrmion, the green is the Skyrmion velocity, and the red is the Skyrmion Hall angle. So we have a regime where the system is pinned, and then you have a creep regime where the Skyrmions are moving, because they're doing this sort of integrated jump-like fashion. But within this creep regime, the Skyrmion Hall angle is actually zero. And then once they start going more of the flow regime, then you start getting an increase in the Skyrmion Hall angle, eventually high enough drives, and the Skyrmions moving fast enough to get to the intrinsic. So if you go down here, what does the Skyrmion velocity look like? So this is a plot of the Skyrmion velocity. So basically, the pin, then you get these jumps. But these pin regimes, sort of that's what the system is allowed to relax, and that's sort of more of a dissipation dominant. As you go to higher drive, you have more regimes, more instances of the Skyrmions are moving. I'm going to show you that. So this is the case of the creep regime. glass system. The drive is in the X direction. And you can see that you have to do a pin, and every now and then the whole glass jumps. It jumps in this avalanche-like fashion. And you can also see that the Hall angle is essentially zero. The skyrmion is moving in the direction of the applied drive. So next, we're going to go to the same exact system, go to a higher drive. And that's it. So here, they're beyond the creep regime. And now you can see that they're moving at an angle. And in fact, if we go to a higher drive, this angle itself will gradually increase until it gets to the intrinsic value. And we saw this already. And of course, so experimentally, you see this. Well, so that's I showed this yesterday, but I'll show it again. It shows sort of two effects. One is that at low drives, your skyrmion is moving in the direction of drive, but you can also see it has this sort of, it's not exactly, it has sort of a thermal-like effect as well. Faster drive, then it starts to move at the Hall angle, the higher Hall. And this is a measure of the skyrmion Hall angle for increasing drive. So we have 0 here, then linearly increases, and then saturates the intrinsic value. But let me show you over here, you actually have a regime where you have a finite velocity, but your skyrmion Hall angle is 0. So that's the clean regime. And I'd also have Matthias to show you that in their work as well, they also solve this drive dependence of the skyrmion Hall angle, although they haven't quite seen the saturation. And then, so that was part-based simulation, but some other groups have done continuum-based simulation. So here's Paris. So this is skyrmion velocity versus drive. So what they do is they change, they have their system has these grays, and they find that as you increase that it's uniform, there's no penny at all, and you have an intrinsic Hall angle of about 75 degrees. You start changing the grain size, you increase the penny, and then you start off from the lowest skyrmion Hall angle and gradually saturates to the intrinsic value of the skyrmion. So once you accept that you have this strong drive and this skyrmion Hall effect, it has all sorts of implications for different kinds of dynamical systems. So previously we showed you where you had randomized insights. But suppose you had a periodic array of insights. In that case, your skyrmion Hall angle will now be quantized. It won't just change continuously. It will change in this sort of step-like fashion, and that's because the skyrmion will like to walk to one angle, and then as they go faster, they want to go to a higher angle, and then you'll see a jump in the direction of motion. Now back to the random penny system. So this is the same system you saw earlier. You can then map out a general dynamic phase diagram. So this is the pinning force versus applied drive. So if your pinning is weak, you're in what we call a pin crystal phase. You apply a drive, and then you will pin into a moving crystal phase. On the other hand, suppose you have very strong pinning, your skyrmion lattice is destroyed. If you do neutron scattering, you'll see a ring. If you apply a drive, this thing ends up pinning into sort of a moving liquid phase. But once the skyrmions are moving fast enough, they don't see the pinning as much, and you go back to this moving crystal phase. So this might be some of these samples where people don't know their skyrmions. You might think, well, maybe they're delayed or something. If you try applying a current, you may be able to see a moving crystal phase with the higher drive. And then you can shut your current off, and then the skyrmion lattice will be there. Here's you can also look at this as a function of skyrmion density. So low density, the skyrmions are far apart, the interactions don't matter so much. You go to glass phase, when you increase the number of skyrmions, you start strongly interacting with each other, they want to form a crystal phase, and then at higher drives, you have the moving lattice phase. So let's go back to this picture here. We want to get some insights into moving the skyrmion themselves. So what we're going to do is we're going to measure the skyrmion velocities, and we measure the fluctuations in the direction perpendicular and parallel to the direction of motion. So this is the plot of the skyrmion velocity versus applied drive. This is the skyrmion Hall angle in the inset, and this is the standard deviation of fluctuations on velocity in the direction of drive and in the perpendicular direction. And this measures the amount of six-fold order. So they're talking in the LANL group where they look at the triangulation. So if you have completely triangular lattice, your black curve measures the number of fractions six-fold coordinated skyrmions that will be close to 1. In this case, this is the overdamped case. So what happens is you start off in a pinned state, it decays plastically, so you have a large amount of defects, and then a high drive, it gradually goes to the ordered phase, or dynamically ordered. But your fluctuations are always strongly anisotropic. You have much stronger fluctuations in your direction of drive than your perpendicular. If you go to the skyrmion case of a skyrmion Hall angle of 45 degrees, again you start off in a low skyrmion Hall angle that gradually increases the faster the skyrmion move. But now your fluctuations, they're anisotropic, so they can distort flow regime. But once it goes to the ordered flow regime, your defect, your fluctuations become isotropic. And that's actually due to the magnet source. I'll play in a minute. And this also shows you get to this dynamically ordered regime. So if we're using neutron scattering of this, what would you see? So this is essentially already been seen for vortex systems, different vortices type of superconductors. Is a low drive when the skyrmion lattice, or the vortex lattice is disordered, you get a ring shape, you drive it faster, you get into a moving symmetric phase, and then even faster drive, you get a stronger drive, you get to moving crystal. In the skyrmion, you see something similar, you see a rotation in the lattice, and you also see the system reorder to a better, more ordered triangle lattice than you see in the vortex case. So why, and then if you go to the moving frame and you try to measure the displacements on the particle in the direction parallel to the drive, perpendicular to the drive, at zero intrinsic Hall angle, the overdamped case, you essentially get the 1D liquid-like behavior. So you have diffusion in the direction of drive, but not perpendicular. But in the skyrmion case, you really go to a moving crystal phase where you have only subdiffusion or no diffusion at all in the moving states. So why is this? So in an overdamped system, suppose you have a particle moving over a rough landscape. What happens is, you slow down a lot when you hit a pin site, you get over the barrier, then you move fast and slow. So the fluctuations you experience are much bigger in the direction that you're pushing rather than perpendicular. On the other hand, in the magnus-dominated case, you will feel forces in the direction that you're moving, but the magnus term will now create velocity components that are perpendicular. So your fluctuations are much more isotropic in the moving state of the skyrmion case than the overdamped case. So that's why you don't have this moving, you don't have the symmetric case, you only have moving crystal. So I'm going to try to show you this. So this is the case of an overdamped system. We're increasing the drive. We have periodic boundary conditions in the X and Y direction. And now you're going to be a moving liquid with plastic phase and have a coexistence of pinned and moving guides. And as the drive increases, you'll at some point the fluctuation, the dynamic fluctuation will go down, and you'll reorder to these symmetric. So what that means is we have one-dimensional order here, but then it can slide past. Such states have been seen many times in various vortex systems. Now we do the same system, but for the skyrmion case. And here's what you see. You have, again, it looks similar in this case in a liquid phase. You can see moving at a little bit of an angle. But as they move faster and faster, at some point they're going to reorder, but they'll order into a moving crystal rather than moving symmetric as we saw previously. Here. So I told you previously we also want to look at some other things like periodic rate of insight and so forth. And we're going to do this two ways. One is with the particle base, there's with the continuum base. And so here's just some initial work we've been doing on the continuum-based simulations. This is using UMax. And what we've done is we've created some spots where the anisotropy is higher locally. Here's the square lattice of defects. And this is for fields such that we have 2 skyrmions for every trap, and you can see we stabilize the square skyrmion lattice. We change the field a bit, and so you would have, say, 1.5 skyrmions per trap, and then we lose the order because it still wants to place a skyrmion on every site, but then there's this other region where I think is actually higher field. It's like some other skyrmions. We can also do 1D modulations where you have strips that have higher anisotropy. And then what we end up seeing is you get almost 2 species of skyrmions. You get some skyrmions that become elongated within the trap that coexisting with more circular skyrmions. So this is, and then we can do something fairly simple. We can just take a single strip and we can see this transition from one row of skyrmion to the high anisotropy strip. And the lower it, then we get splitting, we get a zigzag shape, and finally, low enough anisotropy. And then the next step on these is talk about dynamics and so forth. But this shows you that the pitting can also change the shape of the skyrmions, which can induce additional dynamics. So another thing we want to look at was make a ratchet effect. So what is a ratchet? So ratchets are systems where you have some kind of asymmetry between us. You have some kind of asymmetry. You then apply a drive to the system. On an AC drive, you're going to get DC motion. So in a system like this is the typical ratchet geometry used by people for all sorts of systems, is that your AC drive has to be perpendicular to the direction of your asymmetry to get a ratchet. If you apply an AC drive in parallel direction, the particle will just go back and forth. It will never be a ratchet. However, this Magnus term mixes, causes velocity components to be generated perpendicular. So if you apply a drive this way in a perpendicular direction, your skyrmion will get velocity components parallel, so you can make a new kind of what we call skyrmion ratchet or Magnus ratchet effect. And that's here. So in the inset, this is the AC amplitude, and this is the net DC skyrmion velocity. In the overdamp limit, there is no velocity at all, but when you start cranking up the Magnus term, you get more and more, you get a ratchet effect. And it's also a quantized effect due to the periodicity of the underlying substrate. And these are the kind of orbits you get. So you don't get these simple 1D orbits, you get kind of complicated orbits. And the N is the number of periods of last and translates in one AC cycle. You get 2, 2, or it could be 0, which is localized, or 1. So this is one way you can make sort of a very well-controlled motion of this kind. And kind of running out of time here, we mentioned you can also have a new kind of Shapiro step. So typical Shapiro steps in Joseph's system, your AC drive and DC drive have to be in the same direction, but in the skyrmion system, you can have an AC drive in a perpendicular direction, and you will still get Shapiro steps as well. And then let me just finish here. There's all sorts of things one can try. We can start going to 3-dimensional systems. We also want to try to do something on skyrmion jamming or make a skyrmion hourglass. You look at diode effects and so forth. You can also imagine 3-dimensional systems where you have pinning on top and on the bottom, and then look at things like transform geometry and so forth. You can also have local probes. We drag one skyrmion locally to measure the local perturbation. And if mass is in there, it's not clear whether skyrmions have mass or not. But if they do, then things like nonlinear wave may also be supported and so forth. So thank you very much.
So I'm wondering on the ratchet effect. So I've seen people that have done things like take local ion irradiation and they can change the anisotropy gradually and then have it jump down. So you can make a magnetic ratchet. Would that work?
Yeah, I think so ratchets, the real key you need in them is you need some kind of asymmetry in the substrate. So people make them all sorts of different ways in superconducting systems. So what we did is we just assumed some kind of potential. That you can imagine changing the DMI locally, putting